Welcome, everybody, to our lightning toss session. Every year we receive so many great submissions, and we're excited to be able to offer even more interesting topics to you by adding these additional sessions. The structure of this session is 6 back-to-back 10-minute talks. So we'll go quick, and we'll cover a wide range of topics from new solar features to use cases, toolkits, and more. There's a list of topics. And without further ado, I'll introduce our first lightning talk speaker, Noble Paul from Lucidworks.
Hi, myself, Noble Paul. I'm a committer for Lucid and Solr, work for Lucidworks. So today I'm going to cover what is new in Solr 7. By no means this is going to be an exhaustive list of what is new, because I just have 10 minutes and I will just cover whatever is possible. So I just cherry pick a few items and we'll just talk about it. So yeah, this is a major release which is coming up in 7.0. So we've been waiting for a major release to do backward incompatible changes like this. So we've been moving towards JSON over the past few releases. So we use this opportunity to make JSON the default format. And that means if you want to get XML, you should explicitly ask for it. Then a legacy cloud. You know what is legacy cloud, right? So what legacy cloud is whatever a node says is a truth, OK? And non-legacy cloud is like whatever Zookeeper says is truth. So the only way to get stuff into the state is through commands. So in legacy cloud, you can't just come and register a node without a command. Split on white space is set to false by default in 7.0. OK, so I think these things are like covered in detail in other sessions. We have introduced two new replica types over and above what we have today in Solr Cloud. One is a T-log replica, which doesn't write to an index, but it writes to T-log. Then we have something called a pull replica, which behaves exactly like a slave in the master-slave setup. Okay, so it can't become a leader. So we can just see the featured list of all these things. Okay, so NRT, T-log, and pull. So these are the the feature metrics of these replicas. To use this, you can use these parameters as instead of one parameter called replication factor. We have 3 new parameters for each of these. And when you do an add replica, you can just pass a type, and it'll create that replica. One pain point when you create a collection was like we had to create a config set, and it's a difficult concept. People don't understand what is a config set if you're new to Solr. So as a part of the effort to make Solr more easy to understand, more easy to use, so this is one of those efforts. Like now we have a default config set created by default. So if you just create a collection, it'll just do the right thing, using the default config set. So now that we have also removed the manage, what's called manage schema, there's a new collection, new config set for that. That's been removed. Then there's a the next big direction for Solr has been like, how do you manage large clusters automatically? So this actually paves way for lays the ground for new features which are coming up in the subsequent releases. So auto scaling, the first set of features is going in 7.0 is we have a new way to specify how your cluster should be arranged. So where a replica should be created, which node should be created. So this will eventually replace the old replica placement rules. So we have new and improved syntax for specifying this stuff and a new engine to compute this stuff. So in 7.0, what we have is we can specify these rules, and this will be used in all the collection commands like create, add replica, create shard, split shard, and all the stuff. So whenever you create these rules, they all go and get persisted in the Zookeeper in a file called autoscaling.json. So what you see is like a sample autoscaling.json. This is how it looks like. And there are commands to actually create this. Okay, so I'm not going to explain all those commands. I'll just explain what these are. So there are two aspects to the rules. One is how do you tell the system which is a heavily loaded node or which is a lightly loaded node. So basically, it's a sort parameter for identifying which node is loaded more. And what we can do is only this. We have these 4 different choices. Like these are the preferences that we have, and you can choose one or more of these, and you can change the order in which they're applied, and you can choose the position value. So the position value is nothing but how do you now when you say like okay, if you say free disk is equal to so position is for a free disk is say 50 GB. That means if the free disk space between 2 nodes is less than 50 GB, they are considered equal, and we just go and check the next one for sorting. Okay, so this is to create ties so that multiple sorts are applied. Then we have the policies. These are kind of filters or conditions that you apply for where the replica should be placed. For instance, there's a node level condition which says like, okay, don't put more than 6 cores in a node, okay, in any node. That's one such condition. So another example you can see in this one is, say, put all the replicas in nodes with free disk greater than 300. So it says like a replica equal to 0, free disk less than 300. Like don't put any replica in a node which has free disk less than 300. Okay, and if you look at it, there's a parameter called strict equal to false. That means okay, try your best to do that. If you can't do that, still do something. Okay. So there are so in this case there's something called tag. So this is a qualifier. The free disk is a tag, and you can use any of those items in the blue boxes, like the node, host, port, to add conditions. So and we are adding more stuff, and in the future we'll be able to use any metric available in Solr to make these conditions. So this is like a very powerful syntax to dictate where your replicas should go and live. I think, thank you, done, okay?
Long day, wow. So thanks everyone for coming. I'm going to talk quickly about our experience with search and accelerating data science at the 21st Century Science Center for Cancer Research. So again, thankfully this is very short, but we have some interesting challenges in life sciences with both managing data and organizing data. So this is just a very short talk about some of the challenges we face and how we see search really fitting in our goal towards 21st century science. So the Fred Hutch Cancer Research Center, based in Seattle, Washington, is a national research center focusing on the prevention and treatment of cancer. The main characteristic for us is that we're still 20th century science. We're still very much lab-oriented. We're still very much specimen-oriented. We're still very much in the model of treating, testing treatments in cancer with the old model. Primarily, in what I see, is the desktop model. We still use desktop tools. We still use R and Python. We are starting to use some of the distributed tools, but our big innovation in the last 5 years has been giant hard drives, just giant amounts of storage space that we can attach to these systems. So as we go from 20th century science to try to modernize to the 21st century, we were struggling with the same problems that I think you've heard all day. So our data volumes are not unique, but we have lots of data coming from machines and lab devices, next generation sequencing, genetics and genomics data that's really putting a burden on teams because we're now having to deal with data at a rate that's ever increasing. So we're just the same as everybody else. We have a huge data tsunami problem. Especially so that we have to move to 21st century science. Our old mechanisms of thinking, our old approach of thinking of desktop isn't going to work as we try to scale this. But even harder is the issue of data silos, right? We're 250 labs who basically work with a PI and a small research team. That's how science is done within these small teams. So these data silos can either be fantastically innovative with data with computer science, or they can be very focused on biostatistics or some area with no data management capacity. So we have a challenge of not everybody has the same level of expertise in handling data. 20th century science, that didn't matter too much, right? We could do that in a silo. 21st century science means we have to think about standardization, interoperability, and scale. So our easy data problems are the typical ones in that we have more data than we can analyze, right? Generating NGS sequencing data, generating genomics data, we can't actually get through that data set without automation, and even then we only get through part of it. Because we're dealing with medical data, we have hundreds of samples of huge DNA sequence, things like that, that we have to trace, we have to keep track of, both for the testing and treatment models, for the protocol models, but also just so that we can keep track of reproducibility if we need to go back and find those records. We have very big challenges with standardization. As I mentioned, 250 labs. That data really doesn't go very far between those sides, mostly because the metadata, the definitions, even the model of the machines being used to generate the data doesn't allow us to interchange that data. And lastly, because we're dealing with medical data, we have very complex security requirements. Who can see this data? Who can't see this data? How it's traced, how it's audited, what fields are available, things like that. And we have to go through a very deep audit process to make sure we're meeting compliance requirements. That's the easy part. The hard part we struggle is that 20th century science is about ownership, right? You've got a grant, you built your machine, you built your team, you've got your data. That data is heavily attached to your research. It's heavily attached to your grant. The last thing you want to do is have someone like me show up and say, hey, can we share this data? And it's like, no. Maybe the papers and the results, but definitely not the sample data. And the other hard problem is reproducibility. So those of you who are familiar with science, reproducibility is a huge challenge because we can't go back and get the same values more than once. You think that science would get that, but it's actually a huge problem. The data samples drift, the code models drift. We use different models, different libraries of the packages and things like that. Turns out that reproducibility is one of our biggest challenges. So, okay, research teams are coming to us saying, help, we're dying. We can't handle this data, or we can't get reproducibly right, or data management is really a mess. We have to move out of 20th century science. We have to think about 21st century approaches to data management. So being on the technical team, we're like, okay, let's do the cloud. Cloud is an amazing opportunity. High scalability, high capacity, huge volumes. The vendors are really happy to come help lift our data in the cloud. So we're definitely moving towards cloud everything. Cloud data storage, cloud services, cloud compute. On the reproducibility side, we're looking at containers. Docker, Kubernetes, things like that. Container orchestration is our big secret weapon for how we manage reproducibility, because we can contain the libraries, the classes, and parts of the data into componentized, containerized pieces that we can reference and lock down in version. We have to do a lot of work on data management support. What that means is, where is the data? How do you name it? What's the metadata? What's the security attributes? Where are you putting this data? So data quality, data governance, master data management step in a big way. For science teams who are academic, this is a cold shock. They do not like data governance. But it's part of the effort that without it, we won't have a good structure. Lots of training, education support, and then security infrastructure so that we can put a better infrastructure in place for doing the right thing by default. So the question, though, is when we're standing at the technical team, is that really going to address the problem, right? what we're hearing is that we are not able to keep up with our data, and what we're doing is we're throwing a bunch of technology at it. And I said, that's not going to work. We're actually even not going to even bend the curve. So stepping back and saying, we can throw all 21st century data technology, but we're really missing the opportunity, which is that in order to address most of the data problems really stem from understanding how to organize data. So we see search as a fundamental secret weapon that we can use to address a lot of these data management problems, can solve a lot of just the simple basic problem of moving to 21st century science, but really thinking beyond the desktop paradigm to a virtual asset, being able to search on metadata, being able to search on recommendations, being able to use intelligence and artificial intelligence capabilities is really our secret weapon, because that takes us away from where's my files, or where's my folder, or so-and-so left and I can't find anything. That is the culture that we have that we're trying to move off of. More strategically, looking ahead, the big players in data systems and funding, really NIH, National Cancer Institute, and many other academic institutions are saying, hey, why is this problem being solved independently? Why aren't we thinking as a national initiative about how we do this? So there's this big initiative related to what's called the BD2K, or the Big Data 2K grant funding. And University of Chicago and Stanford and other institutions came out and said, what we really need to talk about is not more technology. We need to think about thinking about data. We need to think about data management with the fair data management principles. So I'm not sure why they came up with that name, but it helps to think about, for every data that we, whether it's sample, genomics, databases, clinical data, notes, and things like that, we address that with, is it findable? Is it accessible? Is it interoperable? And is it reusable to really apply conceptually how we should manage data, not just more technology? However, the goal of that data management approach, the goal of FAIR, is to get to automation. And this is where tools like Fusion and Solr come in. This is where, once we've addressed some of this organization metadata, as we start to organize our data out of those data silos, then we can apply automation, whether it's metadata management assignment, search and indexing, format structures, and then applying a common security model. So the goal of FAIR isn't just to do better data management, it's really to move us to where we can start doing automation. So, great, you guys are going to use search, but that's not the whole idea. Search for us is more than just keywords. Search for us is just more than just metadata. We really see that as now an emerging platform. So whether it's internal data within our researchers, like that's such a problem, but also external sources. How do we reference that data with external publications so we can correlate that data? So this is the challenge of 21st century science, how to accelerate science. Not with better data management, but with better correlation, with better search, with better understanding, by finding papers or samples that relate to what you're doing that you can collaborate on. We do a lot of work with NLP data extraction. How do we get notes out of locked and structured data? So things like clinical notes, medication orders, discharge notes, all that have incredible information in the treatment and care for cancer patients that we have to pull out. I won't go through all these. A big one, though, for us is the data platform with search takes us towards data science. Data science and science, I'm told, the scientists say that since we're dealing with data, we're data scientists too. The challenge, though, in 21st century data science, we think more about scalable systems, more machine learning algorithms that we don't use in current data management practices, and we really need to be able to seamlessly move to that to take advantage of those algorithms. So super quick, Solr and Fusion offer amazing technology, but we need your help. The technology for us, coming new to search, is complex. Just even this first day, it's hard to keep up with all the terms and things like that. So the complex implementations are going to be difficult for academic organizations to get up to speed on. And the second big one is the community. We're all in on search, but we're also mostly looking at community. We're, again, academic organization working with large universities. That community of common practices is really important, so it's great to hear the commitment from Fusion on that. And finally, cancer is not a technology problem. We use technology, but cancer is a people problem. And every day, Fred Hutch Cancer Research Center works to make a difference in cancer using tools like Fusion and Solr. Thank you.
Good evening, everybody. My name is Ishan Chattopadhyay. Here I have with me Vivek Narang. I'm a Lucene Solar committer. I work for a company called Unboxed. I'm a solar consultant there. They are an e-commerce-based search and discovery platform. Vivek is a student at the University of Georgia. And we're going to talk about the solar benchmarking suite that we just worked upon. So the agenda for this is the Google Summer of Code project. It's a program where Vivek participated as a student, and Mikhail Klodnev and me were the mentors for him. We'll talk about the goals of this project and also about the benchmarking suite in general, and also what remains to be done there. This program called Google Summer of Code is sponsored by Google. It's a 3-month program starting from June 2017 and 3 months down the line from there. Vivek applied for this program, and the idea was to build a benchmarking suite. Mikhail Klodnev and I, as I mentioned, were the mentors. The hardware for the development, the staging server, the production server, those were sponsored kindly by the company called Unboxed. So the goals of this project was to set up some measure of performance monitoring as development happened, commit after commit, release after release. There was some cool stuff already there for Lucene, but something that was standard to be run on Solr commits and Solr releases was something that we wanted to build upon. So continuous integration, monitoring. We wanted these metrics to be reliable and also reproducible. So understood that reproducibility is something which is hardware specific. So if you consider a particular box, you run the benchmarks over and over on the same box, the results are expected to be reproducible. Configurable and extensible, because you'd want to add new features to Solr, and you'd also want to keep building upon those features in the benchmarking framework. So that was something that was an important goal for us there. And support developer workflows. So not only the committers or the contributors to Solr who will benefit from having this running on their laptops or their development boxes, but also external plugin developers who could also take advantage of this benchmarking suite. And this is where Unboxed as the company has a lot of interest in this. And here is why they tried to sponsor this. The Solr benchmarking suite is something that Vivek is going to talk about, so I'm going to hand it over to him.
Thank you, Sean. Hello, everyone. My name is Vivek. I'm a student at the University of Georgia. And I worked on this project this summer. I'd like to thank Lucidworks and Unboxed for making this trip possible for me. I'd also like to thank Ishan and Mikhail for mentoring in this project. I'd like to elaborate on the details for this project. There are two main aspects to benchmarking when you want to figure out what the performance of Solr. So there are two main aspects, indexing and querying. So for indexing, the suite measures the throughput in documents per second for standalone and cloud configurations. And for querying, the suite measures the QPS for queries like the numeric query, text and string queries, highlighting and faceting queries. So here's a quick outline of the benchmarking process. It all starts with getting the latest code from the repository, building the package, and then using that with benchmarking data, in this case, modified Wikipedia data. And the process then generates the benchmarking metrics that are captured in a CSV file. And this CSV file is then used for generating the graphs. So here is a quick screenshot of the web interface that this suite has. You can see that the graphs are published on a page. You also have options to navigate to Solr Wiki and Jira pages. You have options to get details about the environment of the benchmark platform. The metrics are grouped in two. They're in two groups: the standalone and the cloud metrics, and you have options to navigate through them as well. So you have an additional option to dig deep into the process. You can hover on the graphs and click on the graphs to get more data like the heap utilization, the CPU utilization, and other relevant information for that benchmark cycle. And with this, I'd like to hand back to Ishan. Yeah. Thank you.
So next up is how do we configure this benchmark suite to run more and more benchmarks and existing benchmarks. The idea to have this configured is that the user or the developer who is trying to use this benchmarking suite need not go ahead and change any code. The configurations for his benchmarks should be supported in a more configurable way. So towards that, if you can look at this snippet just briefly over, there are a couple of sections in the config.json of this suite. One is the indexing benchmarks, one is the querying benchmarks. The indexing benchmarks take a list of all the kinds of different benchmarks that you'd like to do. The output of those will be maybe the throughput, the latency, and all of that. There's a concept called setups. So for every benchmark, you might want to do that indexing on a different setup. So by setup, we mean a different combination of number of shards, number of replicas, and also the number of threads you'd like to do the indexing with. There's this other concept called query benchmarks, which leverage upon the indexes that have already been created during the index benchmarks. And in query benchmarks, you could configure something like what kind of a client you'd like to use, what kind of the file that the query benchmark would use in terms of firing those queries, number of threads, and what would you call those queries. So this configuration points to the Wikipedia Wikipedia dataset that is indexed by default. There's another contribution from Alexandre Rafalovic, who has kindly helped us out with the Git commit logs, which is also another supported dataset, which Vivek has also worked upon. Next up is the roadmap. So better support for extensibility is something that I just talked about, having it as configurable as possible. We could do always much better than what we already have. The second thing that is a bit interesting for not just Solr developers or Solr committers and contributors, but also companies who'd like to do, maybe who are running on Docker or AWS or Kubernetes. If this suite could provision the nodes on different orchestration layers and do the benchmarks there, that might be very useful to those companies. As of now, what we have currently is the host that this benchmarking suite runs on spins up different Solr nodes on different ports of the same host. So this doesn't reliably maybe replicate the scenarios where you'd like to do indexing on one box or reading on one box, or maybe you're reading from a hard disk and writing into an SSD. But having such support to provision nodes on the fly would be beneficial, and we'd like to have that. Another thing that we'd like to have is to add more Solr features into. So if you look at a few slides back, these are the features that are already there. There are many things that we'd like to build upon. So for example, block join, spell check, the new replication model that Shalin and Dart talked about, and Thomas would be talking about tomorrow. That is a prime candidate for adding benchmarks for. And of course, we could add more data sets. Currently, we have Wikipedia and the commit log. More interesting data sets might help us bring upon more insights into regressions or performance improvements, commit over commit, feature over feature, release over release. So this is what we were working on. Thank you to Google for sponsoring this, and thank you to Vivek, who will be continuing to work upon this. Thank you very much.
Good afternoon, Solr Lucene Revolution. My name is Marco Baldino. I'm from the MITRE Corporation, and I'm representing the OpenSextant project today. Before we begin, I'd just like to dedicate this to my sisters, because everybody needs a little Las Vegas luck every now and then. Okay, so a quick agenda. I'll give you some history about why Solr and the Solr text tagger, which I'm going to talk about in just a few minutes, are game changers for our solution design for geo-tagging. So yes, I'm at the right conference, I know. We're talking about geo-tagging and NLP purely, but there's a whole lot of Solr and Lucene technology under the hood. And then I'll talk about some applications that'll be relevant for you. So OpenSextant, it's more than geo-tagging. It's a lot of information extraction technologies and algorithms and techniques that came out of some government work, some MITRE corporation internal R&D and prototyping over many years. We decided, we converged a handful of projects, got together, collaborated, decided this is good. This is going in the right direction. We don't have to do it again and again and again as we had been. We decided to open source all that goodness that came out of it. A byproduct of having done that is this thing called the Solr text tagger. And if David Smiley will just raise his hand, author of that one, thank you, David. The text tagger, it tags text. It tags it very fast, and we'll see that in just a second. So, but before I get into the text tagger, let's do a quick primer on geocoding and geotagging. So let's say you have some text that you want to process for geography. It's just getting any kind of geographic cues out of that text as you can. The text is in some language, it's in some character set with some script, something that you're familiar with or something you're not familiar with. It could be Asian scripts, could be Ukrainian, so on and so forth. Take that text, you want to mark it up for known places of interest, whether those are publicly known places or things you have in your private catalogs. And then finally, you want to code it. You want to code it for location, you want to code it for other metadata. And deciding which exact location you want to associate with the mentions in the text is one of the hard challenges. So yeah, putting that push pin on the right, Bugny-les-Gamaches in France, as opposed to the one next to it, it takes a lot of effort. Place names like Esperanza, Springfield, Mohammed, these are all common place names dotted around the planet that they just appear again and again. And if you don't have enough context in the input signal, whether it's some metadata around the document or actually in the document, you're not going to be able to disambiguate which exact Springfield, which exact Mohammed we're talking about on the planet. So some of the drivers for geotagging here are the immense amount of reference data that you could have. As today, we have about 17 million place names. It's actually 17.5 million place names in the catalog of geographic names. This is a gazetteer. It represents about 10 million locations around the world. And over the last 5 years since we've been working OpenSextant, that has doubled. So I can imagine the next few years, it's only going to increase. Those names are in many different languages, and so is our input text. It could be any number of languages, but about half the world speaks about 6 languages. The other half, there's another 80 or so that are probably active. Don't quote me on those numbers, but that's very approximate research. The best expertise, the best technologies to do geotagging and this sort of geographic information enrichment cost money. They're not free. There's a lot of investment put behind them. And they also generally involve connectivity. So what about the folks in the field? I'm a humanitarian with a laptop and I have no comms. What do I do? Can I geotag data? Probably not, if I'm relying on something that's connected. So quickly looking at the layout of an OpenSextant application. Well, Solr's inside. Whether that is an embedded Solr or that's a remote server, either or, the best option is to have an embedded Solr server baked into your application, and this is pretty much what you see. This would represent what's on disk. This is all self-contained, more or less. So Solr is the platform. clicker. Oh, there's a couple clicks. Oh, they're coming up in pieces. Anyway, so Solr as a platform is very powerful and extensible. And through the library, Lucine's finite state transducer library, we have the Solr text tagger doing what it does, because it bases its sequence matching off of that library. And that's as much as I'm going to say about that. David has a 2013 a talk from a couple years ago all about the Solr text tagger and finite state transducer. Very good. It's online. Please take a look. It's compact. The gazetteer, those 17 million names, about under 3 gigabytes, all said and done. And in memory, that thing just loads up in about a gig of RAM. And it's fast. Next. I think I'm running out of battery on the clicker. No, I'm not. And we, back a couple. Shh. So anyways, boom. So we got all these benefits from actually using Solr. This used to be commercial entity extractors, databases that you got to install, lots of data curation, very complicated platform to actually make an actual geotagging solution. But now we have something that fits on a thumb drive and can operate on a laptop or a server in a data center here or someplace out remotely with no comms, or you could configure it as a MapReduce or some other sort of batch big data job. I'm just waiting for the clicker. Thank you. And again, don't give away the surprise. So let's look at the text tagger in action. We wanted an API that was as simple to use as could be. You put text in, you get back out geocoded mentions. So let's look at how that actually happens. The tag operation is a Solr request handler that provisions a Solr text tagger plugin. That plugin taps into our gazetteer index. That's a Solr index that has all that rich metadata, all those point locations. It's actually got spatial for J, which is another Dave Smiley artifact, baked in there for geospatial search against that data. At runtime, the text tagger pulls out some default configuration from the Solr config, and the input text, some other parameters for tuning, and then we get two things out of that. Text spans, which are mentions or pointers into the document, and then the metadata from the gazetteer index. So the text tagger is matching anything that's in your input signal and finding what matches you have in your gazetteer index or your reference data. And that could be any data. That's just for geocoding and geography. It happens to be a gazetteer. So first, before we can make use of this intelligently, it's helpful to filter the things that come out of the text tagger. As I think Adele said once, just because you tagged it doesn't mean they meant it. So anyways, my daughter could sing that much better. But rumor has it that the Solr text tagger will just tag whatever you feed it. If it's in your input signal and it's in the gazetteer index, it'll match and you get it. That's good and bad. It requires some filtering on the end there. We assembled the results back into a logical data model called a candidate. These are place candidates. It's not a done deal yet. It's just the initial part of the solution. So we found the things we know about, and then we enrich them and return them back in the API. So we take that output from the text tagging phase, now we go into the geocoding phase. So first we do some more application of rules, heuristics, and filtering. We can tag for nationalities and countries, apply some more interesting language-specific stop terms, things like casa. Well, it's an actual place in the Latino world, but it's also a ordinary noun. It means house in Spanish. So that sort of thing gets filtered out. We can tag additionally for well-known persons and organizations that we know may or may not be places. So if they align and overlap, we'll filter them out. And then we apply our geocoding rules. So for example, if we see Las Vegas, comma, Nevada in our input text, well, I can make use of the geographic hierarchy there that says Las Vegas. Well, the one we want is the one that's in Nevada. great, as opposed to one of the other 200 Las Vegases around the world. That's all about disambiguation. So we score the candidates, bring them back. Now we have the primary output of all this, the tagging, the geocoding. It ends with returning geocoded mentions of data back to your caller, along with, to boot, related persons and organizations that we found from that additional phase there. And all this was all about building context around the data so we could provide better evidence of why we're choosing a location or why we're filtering in or out particular data that's been found. So Solr and Lucene are wonderful at their job. The text tagger is very great recall. We measured it around 98% recall, but with excessive noise. It's great speed, too. The geocoding helps us improve the precision of that capability. So all that filtering, all those rules have been applied, and all that evidence comes in, and we can actually measure our precision and provide some sort of confidence about all that geocoding. Here's just some components online. Our GitHub project is active, and there's a lot of richness there. We're making use of a lot of other open source components. I'm the author of the exponents module. It's kind of a Apache licensed extractor project. The toolbox, OpenSextant toolbox, is a gate-based extractor project. There's more GPL code there. In exponents, I've demonstrated more direct use of the Java API, wrapping it as REST, building a MapReduce capability. Very simple stuff, but very powerful and very fast. So applications for geocoding, you name it. If there's anything to do with geography that you want to find out, tourism, park service, humanitarian, so on and so forth, by all means, contact us first if you want to make use of the projects. It helps, because we don't have the downloads already. We can facilitate and engage you into discussion and getting you there to where you want to be. So our brothers and sisters down south of us suffered a massive earthquake 2 weeks ago, last week. So I decided to use that article as an example to show, download one article, process it, visualize it. What did I learn? Okay, I could do this for millions of articles on a daily basis. Doesn't matter, I just want to show the concept of the tagging. Let me visualize it, inspect the content, see that it's good, and then coding it, visualize it, inspect it, do something with it. Now I'm that much smarter. So in summary, OpenSextant is more than just geotagging. A lot of benefits from the text tagger and the Solr platform in general. It's flexible, extensible, compact, works well with memory. Very excellent multilingual support. And by and large, OpenSextant will help you discover worldwide geography in any of your data, in any language. Thank you.
Hey everyone, wow, the lights are bright up here. My name's Mark Miller. I work for Cloudera. I'm a software engineer. I'm also a Lucene and Solr committer. And I'm going to talk a little bit about the project I've been working on over the summer, which involves trying to stabilize Solr and Lucene's test situation, which is something I've been working on for a while and with mixed results. And so I'm going to talk about a tool that I've kind of been developing over time, but finally crystallized what I wanted to build and put in a bunch of time over the summer to do it, and I call that tool Beastit. So the tagline of Beastit is basically run, test fast, generate test reports. And the reason it's important to run test fast is what I determined is that the best data that I could get on tests was kind of deep data on single commit points. Part of the issue with just having Jenkins send fail emails to a dev list is that the code base that Jenkins is generally running tests on is kind of changing by the hour, by the day, by the week, and so you're kind of getting these results based on a moving target. And so over time, I've grown to like the idea of having deep data on a single commit point, so you know exactly what you're working with, and then having data for commit points over time so that you can do comparisons and see how things are changing. So why I've been working so much on trying to improve flaky tests and stop seeing so many fail emails to the dev list from our Jenkins cluster. There's a lot of difficulties right now in our current testing environment. Many years ago, we looked at speeding up tests because a primary motivation for me pushing that was Solr tests started to take over 20 minutes on my computer. And for me, that's just too long a turnaround. And so between some other people already having tried some things down those lines and recruiting a few people, we moved to parallelizing our tests so that we can run a configurable number of tests at the same time. Around that time, we also started introducing all this randomized testing, where we will randomly pick implementations and randomly pick different code paths and tests so that you can explore basically a larger subset of the known configuration and test space, et cetera. So between these things, it became more like a SETI at home project in terms of running tests. You're looking for different fails based on all this randomness. And so we started running our Jenkins jobs instead of once a day, like continuously. As soon as it finishes, run it again. So now you're cranking jobs all the time, and we started running them on more than one server. And so we have a variety of servers now that run them, and they run them with different JVM versions, and they run them on different OSs. And so there's just tons of variability and configurability. And all of those different Jenkins instances point all of their fail emails to our dev list, and so we see them kind of pile in for a variety of reasons. Some of them for test bugs, some of them for real bugs, some of them for environment issues, some of them depending on the OS. Like all sorts of different issues. Some of them just because the tests were not very stable, were not built very well, would need a lot of improvement. So we have all this data, we have tons of data flowing in all the time, but we really don't understand it very well or understand which tests are the worst. I mean, sometimes you get a feeling because you see a test name very commonly, and sometimes that's changing over time because people are committing things and there's multiple branches. And so we have tons of data and very little insight. So I've been trying to work on that in various ways over the years. And a lot of the ways we've been trying to tackle tests really is following the dev list. You pick an email of a test that seems to commonly fail, and you spend a lot of time trying to iron it out and make it better. And you can make a lot of progress that way. But the problem is, as soon as you stop, instability tends to creep in fairly fast again, and you're basically right back where you started. The problem is not only the introduction of new flaky tests, but changes that make older tests flaky that people can't really see or tell. They're introducing these bad changes over time. So what do we need to solve this? We really need to know what are our most flaky tests, what tests we need to actually concentrate on, not because they fail a lot because of some environment or because of what OS, but because in a well-configured, good environment where we know they should run, they fail a fair amount of time, some percentage of time based on how many times you run it. And what we'd really like to is a history of each of these tests over time at a commit point, so you can make really intelligent comparisons over time and see which tests are getting worse and which are getting better. And so that if things start to destabilize among a variety of tests over a week, you can say, wait a minute, somebody has introduced something here, and we can tell. And it can be hard to tell just by looking at running the test a few times yourself. To get a good idea of true testability, you really have to run it maybe 300 times, 500 times. And even then, sometimes you'll find fails that only fail 1 in 300, 1 in 500. So to be even more sure, maybe you want to run it 1,000 times. And running a test that long, some of these tests take 1, 2, 3, 5 minutes to run. Running a test that long is tough. So one thing you really want to do is run tests in parallel. It has a couple advantages. One, there's a lot of really fast hardware that can run many tests in parallel now, and so you're kind of taking advantage of that, and you're speeding up how fast you can run through a number of iterations. And two is now the test is competing with itself for resources, n number of times. And that helps expose resource-bound issues you'll find. We need these tests to run on developers' machines across multiple OSs, across all sorts of amount of power, number of cores, amount of RAM. And so you really want to be able to run that test and see what it's like under a very stressed environment, so you can see what fails come out and actually make sure it's a hardened test, and that you're not making it so that developers have to wonder, did my change break this? Did my change create this instability? Right now it's really hard to tell. So what you'd like is want a report to go check and say, oh, I just made this big change and I see this test fail. Let's go look at that test and the history of that test and see, does that make sense? Did I introduce this, or does this test kind of commonly fail anyway? So it kind of gives you that, and it also lets you run like you can create a report before and after your change and see what's the profile. Okay, there's some test instability after my big change, but if I look before, it's a similar profile to what was before, or okay, I changed it. Obviously, this test is failing way more. Maybe that's something that I did. So getting this data is kind of hard, it's kind of expensive, running a test. Each test, we have, just in Solr alone, 900 plus tests. If you add Lucene, it's thousands of tests. And so running these for many, many iterations is tough. But I worked on a project to do this where you could like spin up 5, 6, 10 machines in the cloud and then kick off this project that will beast all of the tests and generate a report. It can integrate with BitBalloon to actually publish a website for you if you configure that. And it can integrate with Dropbox so that all the fail logs are uploaded to Dropbox. And then in the fail report, if one of the tests fails a certain number of times for how many times you run it, you can see all of the fail logs and try to debug and make improvements. So the basic idea to do this is it used to be something I had to do by hand that was very difficult. It took a lot of time. I had to kind of tie all these sub-pieces I built together. But at this point, I have it so you run a single command line on your local desktop. It takes your local checkout of whatever project you want to use. It used to be just Lucene and Solr, but now you can configure it for almost any project. I've added support for HBase and Zookeeper and a couple other projects, although I'm still fine-tuning some of that and finishing up. But basically, because I use Docker instead of Lucene and Solr's built-in parallel test support, which is what I used to use with a basic script that I wrote. But now I realize Docker provides much better isolation. It's much easier. You don't run into as many issues like running out of file handles or various things because each isolated instance of Docker that's running each test in parallel is very isolated in terms of OS settings and disk space and whatnot. So basically, you can run this one command and point it at a number of machines, whatever you pick, and it will spread all the tests across all those machines, run them like I iterations, P times in parallel. So I might run, for a common report, 50 iterations, 10 to 12 instances of the test at a time in parallel, and you basically collect the results for every single test and create this report and publish it. And so this report actually lists your worst tests in a good environment, running it 50 times, 10 instances at a time. Here's how often it fails. And so one thing I found out with our Solr tests, which have a lot of fails coming to the email list, is that it's actually, we have 900 plus tests, and the problem tests are generally under 20. So it becomes very easy now to focus on those 20 tests, and not only just focus on them, but focus on them in the right order, because you can see at the top which ones are failing the most, which ones are over 50% failing in those 50 or 100 runs, which ones are over 30%. And you basically have a kill list that you can work down. So like I said, originally this took advantage of the ability of Lucene to Solr to run tests in parallel, but I've changed it to use Docker so that you can basically configure this for any project that runs on Linux or Unix. Right now, it only really works with something with apt-get, but that can change in the future. And so you can really throw any project at this and generate a report once every couple of days, once a week, once a month, whatever makes sense. Not only can you generate reports, but you can also, just as a byproduct, use this to run all of your unit tests across, say, 10 or 20 machines, have it done very quickly. Just do it one run for each test and get like a report just like you did ant tests, but much faster across a variety of machines. There's a lot more that can be added too, but that's what I have so far. Yeah, and so that's Beastit. There's a lot more to it. There's a lot more I could talk about, but 10 minutes is not very much to get into it. But I'm pretty excited on the potential for it to really rain down the number of fails that come to our email list. I've done a little bit of work in the past that's had good results, and now I just have to start cronning it so it runs regularly and make it more of a big deal to get committers involved in ignoring tests that are failing too much or fixing them. But that's about where I'm ready to focus on right now. And that's it. Thank you.
Okay, hello, my name is David Arthur. I work for Lucidworks, and today I'm going to be talking briefly about some of the stuff we've done while building Fusion. Not strictly a Solr talk, but there is a slide on Solr. So yes, again, my name is David. I'm the engineering manager for the core team at Lucidworks, working on the Fusion product. And I've been working on it since before it had the name Fusion, basically. So from the project perspective, there's about 27, roughly, engineers working on Fusion. Around 300,000 lines of Java code, about another 100 or 150,000 lines of test code. 70,000 lines of, some UI stuff that I don't really understand. 6,000 lines of closure, which I'm not really sure how that happened, but it's there. And I mentioned here at the bottom also 50,000 lines of Python, which is just test code. It's not production code. It's just test. And there's a slide on that later. So everything is in one massive repo. Used to be split into lots of different repositories, each with their own build and publish, and this was pretty much just a nightmare. A lot of times we feel kind of that urge to go back, and we have to resist because we've been down that path and we know that the problem's there. Everything is written, the whole build is written in Gradle. It was, once upon a time, a mixture of Ant with checked-in jars, Ant and Ivy, and also Maven. And we have around 70 Gradle modules, if you're familiar with Gradle, so it's quite a few. However, once you're kind of in that world in Gradle, everything tends to get a lot simpler. So we have one task we can run, which will do basically the whole build, one task to run all the tests, one task to produce the artifacts. So it's pretty convenient. The IDE support is okay. It's not fantastic. It's a big, complex project, but it's getting better every day. We love IntelliJ. We use it pretty much exclusively, except for a few people who have held out with Eclipse. Some of the things we win by doing a mono repo like this is we don't have problems with stale versions or caching weirdness. So if one project is building its artifacts, you're depending on it, and another one, you don't have to really question or scratch your head, does it have the latest changes? Or you don't have to do any manual steps to ensure that it just happens automatically. And similarly, there's no need for doing this kind of cross-publishing. So before getting really, or not really low level, but lower level, I just want to say briefly, we embrace standards greatly. We use a ton of them. And these are just a few that are sort of more Java level things, except for JSON schema. But even things like HTTP, which seems like a strange thing to embrace as a standard, but there's a lot in that spec. And when you really follow it and implement it correctly, then lots of things just sort of work and work for you. So we love standards. Zookeeper is a very important part of Fusion. It's sort of the foundation of our distributed architecture. We use it for service registry. We have a distributed microservices kind of architecture, and we use Zookeeper for discovery and service registry and dynamic load balancing, things like this. We also use it as just a storage engine. It's really good for that. It's a very nice, consistent storage backend. So the types of things we put in there, stuff you might normally put in properties files, we have in Zookeeper, so we can dynamically update them, and it'll be reflected across the cluster. Objects, which we call them objects, but it's a terrible overloaded term, but that's what we call them. This is stuff that you might think of application data, so configuration that the user provides, and this is stuff that you might traditionally put in a relational database. We put it into Zookeeper, and so far it works pretty well. There's some other cool things, we use Zookeeper for doing some coordination with locks and stuff like that. Watches are a particularly interesting aspect of Zookeeper. You can learn, go read the documentation if you're unfamiliar. I'm sure most Solr users, though, are rather familiar with Zookeeper. And Curator is fantastic. Curator is an Apache project, used to be Netflix, I think, and it basically kind of hides away a lot of the complexity of dealing with Zookeeper. Zookeeper, while as fantastic as it is, it has a lot of nuance to how to use it correctly. There's a lot of caveats, a lot of gotchas, and you really have to read the documentation and understand it to use it correctly. That said, even using Curator, you need to read the documentation because there are even still some caveats there. And just quickly, the CH root is a nice little feature that we use. Helps keep your data isolated from others in Zookeeper. So for example, Solr has its own CH root, and we have our own, and we never have to worry about colliding with other services using Zookeeper. So as nice as Curator is, we have written an abstraction on top of it for dealing with object storage. We call it Item Store, and it's just a really simple interface. Little example at the bottom there. So you give it a path into Zookeeper and a POJO, and magic happens. We use JSON serialization, and we expose the multi-version concurrency control APIs of Zookeeper, so you can do, like non-destructive updates, basically, the whole concurrency thing. Another thing that, and this is another thing we get from Curator, is caching. There's basically a recipe that keeps all of your, it's called path child cache, I think, or something like that. And it's basically exactly what it sounds like. It's a cache. So for some objects, we don't want to be reading constantly. Like if it's something that happens at query time, we don't want to be looking it up for every request. In Zookeeper, that puts a lot of read pressure on the system, and that can, cause problems. So we use caching pretty heavily. Speaking of objects, one thing we do with all of ours is annotate them with schema. And it looks a little bit like at the bottom there. We have sort of this declarative approach to generating JSON schema. And this has been a huge boon for us. Previously, and I'm sure lots of you are familiar with this, you need to make a small change to a configuration object. So, you can go make the change and test it and deploy it or whatever, and then the UI team needs to go do the same thing. Well, what we've done is basically we've created a UI which is dynamic and will render forms for editing objects based on the schema. So if you want to change like the mouse over text or a description or even add fields or change types, you don't have to make any changes to UI code. It's all schema driven. So that's been a big help. Another thing we've done to help ourselves, this is really sort of the theme of this talk, is stuff we've done for ourselves, is this client proxy. And what it is basically a JAX-RS annotated interface, which you pass into this thing here down at the bottom, client factory, and it generates for you a full-fledged HTTP client. And it deals with our distributed service discovery, so it knows where to go find, where the request should go. It deals with serialization and handling errors and all sorts of stuff. And so instead of dealing with HTTP verbs and serialization and all that stuff, you have Java methods, and it's really nice. Here's my Solr slide. One early problem we ran into with Fusion was compatibility or interoperability with lots of different Solr versions. That's one of our big key things in Fusion is we don't force you to use a particular version of Solr. We support a wide range. And so to mitigate this, we ended up not using Solr-J to do many kinds of requests. So the management APIs, configuration APIs, things like that. We built our own REST client to talk to Solr so we could embed all that conditional logic for dealing with different versions of Solr in our client, rather than having to deal with managing multiple versions of Solr-J, which would be pretty difficult. Another big part of Fusion is our connectors framework, which it's been mentioned in other Fusion talks this week, or today, I guess. And this is something we decided to heavily invest in. We had previously used lots of different commercial and open source projects to provide plugins, basically, for other systems. And we found that just over time, because we've been doing third-party integrations at Lucidworks for 7, 8 more years, maybe. And we found that over time there were issues with quality, issues with support, or projects would just disappear and we'd be left in a lurch. So we've decided to fully invest in our own solution from the ground up, and it's been we basically do it so you don't have to. Sort of touching back on the embracing standards thing, one thing we've done with our security model is we've basically said if something can be accessed through Fusion, if something can be done through Fusion, it has to be expressible through an API call. And so that allows us to greatly simplify our security model to just saying, okay, your permissions are essentially what methods, what HTTP methods you can use and what paths. And we do some wildcard things to make it a little bit more convenient. We decided to do this pretty early in the project, and it's made life very, very nice in terms of not having to deal with all kinds of weird security things. And this is just for authorizations. The whole authentication mechanism is separate. So if you're connecting to your LDAP or Kerberos or all that Realm authentication stuff is totally different. This is just for authorizations. We do a little bit of crypto in Fusion. When you type in your MySQL password or whatever to into a data source, we encrypt that, so it's stored encrypted in Zookeeper. And I feel like this should be said in any talk that mentions cryptography at all, is like, don't do it yourself, right? Use the tools that exist in the community. And so Java comes with quite a lot of tooling for dealing with crypto. We use Bouncy Castle to provide Cypher with a longer key than what Java provides, but we still use the Java APIs for dealing with things. Another thing that we developed, almost as a novelty in the beginning, but it ended up being kind of very useful, and it's one of the most heavily relied on internal features in Fusion. Most users don't deal with this directly, but it's relied on pretty heavily, and it's this blob store, which is basically just a place for us to put really large files. So Fusion, we strive to make the backend stateless, so we don't have to worry about local files and things like that. So we're like, okay, we need to put these files somewhere. Let's try Solr. And that works okay up to a certain file size, basically. And so we built this thing we call the blob store to sit right on top of Solr to give us the ability to stream in very, very large files, well into the gigabyte range. And it performs very well for what it is. And it's not the fastest thing in the world, but it works very reliably. We currently use it for distributing data sets with Fusion. Like when you download it, things get bootstrapped into the blob store. It's where our Spark machine learning models get stored. And with the new TwigKit integration that you saw Will demo this morning, that's where those apps live. Basically, it's like a war in this blob store that gets served up through a TwigKit service. And finally, just a quick note about testing. This kind of gets back to the Python comment earlier. We wanted to have a nice, easy to use, easy to maintain test framework for our API and integration tests. And we basically took a framework called PyTest, which is, in my opinion, regardless of language, one of the nicest test frameworks out there, and built a lot of stuff on top of that to give us really robust tests and promote lots of good code reuse in our test framework and stuff like that. One of the more recent enhancements we've made to it is integrating with Docker. We use Docker widely at Lucidworks. We have Docker images for developers to use that have all the environmental stuff set up. All our builds on Jenkins happen in Docker containers. The demo you saw this morning was running in a Docker container. And for tests, we use Docker to basically isolate services. Like here, I have an example using Postgres. The reason for doing this is so we don't have to ask our infrastructure team to maintain a Postgres instance and keep it up and running, so our tests are all working. We can just bootstrap one very quickly in the actual test, do our setup, do our assertions, and then it'll get torn down. So in this example, it'll create a Postgres instance. You might connect to it from Python, put some data in it, and then configure Fusion to talk to that database, do your JDBC ingestion, and do your assertions or whatever, and then it'll get torn down. And that's all I have. Thank you.